last you may record in the last video that that we did an example where none of the three conditions is satisfied. But if you are to do that in an exam, if you are to do that in an exam, that can be really time consuming, because I mean checking each of the three conditions can take maybe 5 minutes, and so you spend 5 minutes on each. That means you're spending like 15 minutes checking one question, right? Which is a lot of time. All right. So the question is there a way to check? Is there a way to check that whether the extremal types theorem will hold or not? Right. So, and the answer is yes. If you have a variable that is discrete with the CDF f and WF denotes the upper endpoint, then the extremal types theorem will hold if and only if will hold if and only if the following limit is equal to 0, right? Okay, so that's a very beautiful condition. It allows you to see if the limit is 0, that means one of the three conditions will hold, and if the limit is not equal to 0, then none of the three conditions will hold. Okay, all right. So the tutorial that we will do on Thursday will be this one. These are, I know you can't see it now, but we will do that on Thursday. But before I before we do the tutorial, let me do some examples. Let me do some example on all right. The first example, suppose X is Bernoulli X is Bernoulli with parameter P, right? All right, which means that X is equal to it takes the value either 1 or 0, 1 with probability equal to P, and 0 with probability equal to 1 minus P, right? Okay, so the question is, does the ETT hold, right? Okay, that's the question. Okay, so to do this, I'm going to use the condition that I just gave you, which is this one here. I'm going to use this condition here, right? Okay. So to use that condition, first we need to figure out W of f. W of f, remember, is the largest of the x's for which x is defined. In this case, x takes a value 1 or 0, right? The Bernoulli takes either value 1 or 0, and so the largest of the x's is equal to 1, right? So this implies that the limit of the probability that x equal to k right? We're going to look at this. The limit of this ratio as k approaches 1, which is going to be the probability that x equal to 1 divided by 1 minus the CDF at 1 minus 1. All right. Okay, so this is going to be the probability that x equal to 1, 1 minus f at 0, right? Okay, so now this is the same as saying that this is the probability that x equal to 1 divided by 1 minus, now the probability, the CDF at 0 is simply the probability that x is less than equal to 0, right? Okay. All right, so this will be the same as the probability that x now 1 minus this by the 1 minus the probability that x is less than equal to 0 is the probability that x is greater than 0. Yeah, okay. And this is the probability that x equal to 1. Now, if x is greater than 0, then the only possible x can take, if it is positive, if it is greater than 0, must be 1, right? And this is clearly equal to 1, and this is clearly not equal to 0. So the conclusion is that the extremal types theorem does not hold, does not hold. Okay, HOL, does not hold. All right. Okay. All right, guys. So that's the example on the thing that I just on this thing here, right? Okay. So this is just what I have just done is an example on this. So this example says that here for a Bernoulli random variable, that the limit of this is equal to 1, which is not equal to 0, and hence the extremal type theorem cannot hold, right? Okay, so basically it saves you the trouble. It saves you the trouble of not having to check the 3 conditions 1, 2, and 3, right? And okay. All right, now let me do one more example. I hope you, if you have any questions, by the way, if you have questions on anything I'm talking about, not clear, or just use the chat box, okay? Or if you can't hear me on a thing, just choose the chat box. Example 2, right? Now in this example, I'm gonna suppose the following, that x is a random variable with the probability mass function given by okay. All right, so this is the second example I'm doing now. Okay, now again the question is does the extremal types theorem hold or not? So again, you know, this saves you the trouble of having to check the 3 conditions, right? So the first thing you must work out is W of f. Remember, W of f is the largest of the possible values for x, right? So the only possible value x can take here is k0, because it's 0 elsewhere. So W of f must be K0, right? By the way, is the writing clear enough, or is it not focused or not? Hello, guys. Let me know if it's not clear enough, please. All right, so I'm using the same condition as I did in the previous example. So this is the probability that x equal to K0, 1 minus the CDF at K0 minus 1. Okay. Right. All right, now the probability that x equal to K0 we know is equal to 1. Right, so this is gonna be 1 divided by 1 minus the probability that x is less than or equal to K0 minus 1. Okay. Right, so all right, now 1 minus this probability is going to be the probability that x is greater than K0 minus 1, right? Okay. And okay, now once again, if you look at the definition of the distribution, if x is greater than K0 minus 1, the only possible x can take is K0, right? So this is the same as excuse me. This is the same as saying 1 divided by the probability that x is equal to K0, right? That's because of what we have here, guys, because the only value the random variable takes is K0. So if it is greater than K0 minus 1, it must be K0, yeah, okay? And so this is equal to 1 divided by 1, which is not equal to 0, all right? So the conclusion is the same as in the previous example, that the extremal types theorem does not hold. Okay. All right, guys. So that's example 2. All right. I hope is this clear to all of you so far or not? I mean, the reason I'm doing these examples is to help you with the is to help you with the next quiz, which is quiz number 2. All right. Okay. All right. If this is not clear, let me know. All right. Use the chat box. All right. All right, now the next example I'm going to do is a little bit tricky. So this is example 3. All right. Now, suppose suppose x is a Poisson variable with parameter lambda, right? Right. And does the ETT hold? All right, that's the question. All right, now in this case, you remember the Poisson distribution. For the Poisson distribution, The probability mass function is the probability that x equal to k is equal to e of minus lambda k divided by k factorial, right? Where k goes from 0, 1, etc., right? So in this case, so I mean the Poisson distribution is defined on all the non-negative integers, right? So your W of f, remember W of f is the largest point of the domain. So in this case, the domain is 0, 1, 2, 3, etc. up to infinity. So your W of f is plus infinity, right? Okay, so what we need to check, is the following, that the limit as k goes to infinity of the probability that x equal to k divided by 1 minus the CDF at k minus 1. So we need to find the limit of this. We need to find the limit of this as k goes to infinity, right? So that's what I'm going to do now, because this question, as I said, is not as trivial as the previous two ones. Okay. Okay. All right, is this one. Because I have written the CDF at k minus 1 as the probability that x is less than or equal to k minus 1. And this you can write as the limit of the probability that x equal to k okay, as k approaches infinity. Okay, all right. Now in the next line, I'm going to do the following. I'm going to write the probability that x is greater than or equal to k as the sum from I from k to infinity of the probability that x equal to I. Okay. Okay. Now I'm going to substitute the probability mass function. Okay, like this. You see what I've done so far. Okay. All right. You see, do you have any questions? Jatin, why isn't it x greater than? No, sir. That's because, okay, if x is less, x is 1 minus the probability that x is less than or equal to k minus 1 is the probability that x is greater than or equal to k. Because you see, you're taking the opposite of this event, which means that x has to be greater than or equal to k, not k minus 1. You should follow what I'm saying. It is strictly greater than k minus 1, yeah. Because, okay, if it is, you're right, Jack, in that this I could write this as the probability that x is greater than k minus 1, but that's also same as saying that x is greater than or equal to k. You should know what I'm saying. Okay, so I hope you follow what my answer is. All right, so these two guys cancel each other. Okay, all right, so you get, these two guys cancel each other. So in the next line, I'm gonna write this as the limit k approaches infinity of lambda to the power k k factorial lambda to the power I divided by I factorial. You see what I've done. I have these are two constants, so you can cancel them out. All right. So this reduces to this, right? All right. So I hope you are with me so far. All right. In the next line, I'm gonna carry on from this. It's gonna be equal to the limit as k goes to infinity of, you have in the numerator you have this, and in the denominator you have the sum from k to infinity of, you have this k factorial term, which is 1 times 2 times up to k, and then you have 1 times 2 times up to I. Remember, I is always a number greater than or equal to k, right? To the lambda to the power I. Okay. All right. Now you will see that because I is always a number greater than or equal to k, this one will cancel out with this one. The 2 will cancel out with this one, and the k will cancel out with somewhere over here. So basically, the whole of this, right, will cancel out with this, right? All right. So the only thing that remains are the bits here, right? The only thing that remains are the bits here. All right. So you have the following. You have the limit k goes to infinity of you have this one to the power I, right? Then lambda power I. Okay. So these are the only terms that do not cancel out, right? So the terms starting from k plus 1 all the way up to I, and everything else cancel out with the 1 to k here, right? So you have this, right? Now I'm gonna Okay, I'm gonna write each of these terms in a slightly different manner. All right, so I'm gonna write the first term, which is k plus 1, and so on. And I'm gonna write the last term as follows, as k plus I minus k. All right. Okay. All right. Now, because what I just mentioned before, that I is always greater than equal to k. This guy here, I mean, k plus 1 is obviously greater than equal to k. And because I is greater than equal to k, this also has to be greater than equal to k, right? So each of these numbers in the denominator is greater than or equal to k, right? So what you have is that this whole thing here, right, has to be greater than or equal to k to the power I minus k. I hope you follow what I'm saying, right? That is because there are I minus k terms here. Each term is greater than or equal to k. It follows that the product of this term has to be greater than or equal to k to the power I minus k, right? Okay, so that's what I'm going to write down in the next step. In the next line, I'm going to say that the limit of this thing here is greater than or equal to okay. You see what I've done? Because of the argument that the thing I have highlighted in red, the big one, the paper is not clear, sir. It's not clear, is it? Just a minute. It's just a minute. Let me make it clear. Is it clearer now, sir? Hello, guys. Is it clear now or not? Okay, I'm sorry. I don't know why. Sometimes it goes out of focus. Okay, thank you. All right. So because of the argument that I made in the previous step, that is, this whole thing is greater than or equal to k to the power I minus k, you can say that the limit of this whole thing is greater than or equal to this, right? All right. Now I'm gonna I'm gonna do the following. All right. Lambda to the power k. All right. If my writing is not clear, please let me know. Even my eyesight is also very bad, so sometimes I can't see, even if it is not my, even if my writing is not clear, I still can't see it. All right. So what I've done here is to pull out the constant lambda to the power k outside the sum, right? So you see that these two guys do cancel out, right? All right. All right. Now, in the next step, in the next step, we're not far from the finishing line. All right. In the next step, I'm gonna write this guy here as follows: I from k to infinity of lambda to the power k to the power I minus k. Right. Okay. All right. All right. Are you with me so far, guys? Okay. Now, let me know if anything not clear so far. All right. In the next line, I'm gonna make a substitution. I'm gonna make the following substitution: set m equal to I minus k. Right. So I'm gonna make the following substitution. All right. So under this substitution, the above limit can be written as follows. Sorry, somebody waiting still. Okay, you see what I've done? I have made the substitution that m equal to I minus k. So this limit, this expression can be written as this one, right? Now, you may remember this series. This is known as the geometric. Yeah, I am running out of. Well, this is the last step, and then I'm going to this one here. Okay. All right. I know I am going out of page, sir. So this summation here, sir, is the well-known geometric series. I'm sure you must have done that in your calculus courses, right? That if you have a summation like this, this is the same equal to 1 divided by 1 minus z, and this is known as the sum of a geometric series, right? All right, so I'm gonna use that. So if you use that, it's gonna be the limit as k goes to infinity of 1 divided by 1 divided by 1 minus lambda divided by k, right? Okay, now as k goes to infinity, this guy goes to 0. So you have 1 divided by 1 minus 0, which is 1, and 1 divided by 1 is 1, right? So what you have is that the limit is, okay, let me write it down, is 1 divided by 1 divided by 1 minus 0, which is equal to 1, right? So what we have shown, guys, what we have shown, guys, is that we have shown that the limit, I know it's been a long calculations. We have shown that the limit of the ratio we have shown that this is greater than or equal to 1, right? All right, so hence we have shown that the ETT, or the extremal types theorem, does not hold. So these are the 3 examples I want to do. I know the last example is not trivial. I mean, as you've seen, it's not something easy to think of. I mean, if you are given a question like that to start with, I don't think you'll be able to do it without actually getting some hint or something, right? But any questions on this, guys? Hello, guys, talk to me, please. Are you are you okay with this example, with the example that I just did now? Just all right. Okay, thank you. All right, so let me go briefly run through the next three videos. So far only yeah, if if you get a similar question in the exam, I will give you a hint here. Yes, Jatin. All right, now let me quickly run through the next three videos for this week. The second video I did in the YouTube channel is on definition 1 of extreme values. Now, remember, definition 1 says there are the distribution of extreme value can take three possible forms. The Gumbel, the Frechet, or the Weibull. And there are conditions for checking which of the three forms is attained, right? Okay, but in reality, I mean, nobody is gonna spend time checking those three conditions, right? Okay, so the question is there like a way to actually, is there a way to check the three limits, the Gumbel, the Frechet, and the Weibull can be combined into one mathematical formula? And that formula is known as the generalized extreme value distribution, and is given by this following expression here. So this is the CDF of the generalized extreme value distribution. It has three parameters: the shape parameter, the scale parameter, and the location parameter. And this is the notation for a GEV distribution, right? Okay, so basically this formula here, combines the three limits, the Gumbel, the Frechet, and the Weibull into one mathematical form, right? Okay, and then I did this is some stuff on the domain of X. So for when X is psi is negative, the domain is this. When psi is 0, the domain is this. And when psi is positive, the domain is this one. All right. So this kind of summarizes the three different domains of the GEV distribution, right? And then the question is how to, like, how come the GEV combines the three limiting distributions into one? And the answer is here. When psi is negative, it can be shown following these steps, right? That this guy here is of the same type as this one. It's the same type as this one, which is the Weibull limit, you may recall, right, from ETT, right? And when psi is positive, this is of the same type as this one, which is the Frechet limit, you may recall. Okay, and when finally when psi is equal to 0, this is of the same type as this one, which is the Gumbel type, you may recall. Okay, so basically the three limits, the Gumbel, the Frechet, and the Weibull are contained as particular cases of the GEV, right? So that's the summary. So it's a summary of the three statements I just mentioned. Gumbel is the particular case when psi equal to 0, Weibull when psi is negative, Frechet when psi is positive, right? And this is the PDF of the GEV distribution. So it's just simply the derivative of the CDF, you get this, right? And then this is the quantile function of the GV, which is, I'm sure you know what a quantile is. Quantile is basically the root of this equation for XP, is the quantile function, right? And it's given by this, right? By this, right? Okay, and then this is the return level. The return level is a special case of a quantile function, right? So basically, in the case of definition 1, is the level that is expected to be exceeded once in average every t years, right? And so using the quantile function definition, this is the formula for the return level, right? Okay, and these are estimation methods for GEV, right? So I'm using maximum likelihood. I'm sure all of you are familiar with MLE, right? So you have 3 parameters. So the likelihood is a function of 3 parameters, and this is the log likelihood, and these are the 3 partial derivatives set equal to 0, right? And these are the 3 partial derivatives worked out, and you can, there is a program in R. Those of you who are familiar with R, there is a function called FGEV you can use to solve these 3 equations, right, for the MLEs of mu and sigma and psi. Right, so that's the second of the 4 videos. Now the third of the 4th video, let me go through it quickly now. Here we are. This is, remember, this is the definition 2. This is definition 2 of extreme values, where you draw a line which you think is high enough. So if all the data points go above this line, then they are considered to be extreme values, right? So in this picture, you have 11 extreme values, right? So, okay, and so this is basically summarizing the definition of extreme value. Now it can be shown that following the arguments here, that it can be shown that the distribution function of an extreme value under definition 2 is given by this formula here. So this is the formula that describes the distribution of an extreme value under definition 2, right? All right, so I hope you, I mean, if you watched the video, I hope you follow. If you did not follow the video, let me know. I will try to go over this again. So this is kind of summarizing, right? So this is what I just said a minute ago. This is the CDF of the extreme value under definition 2. There are 2 parameters, sigma and psi. Sigma is a scale parameter. Psi is the shape parameter, and this is the notation for this CDF. And GP here stands for generalized Pareto. So generalized Pareto is the distribution under definition, distribution of extreme value under definition 2. Okay, all right. Then here I'm as I said before, this here, I'm talking about the domains of the GP for the 3 different cases. When psi is positive, the domain is from U to plus infinity. When psi is negative, the domain is from U to this, right? And when psi is equal to 0, the domain is from U to plus infinity. So this summarizes the domains, right? Okay, and then when psi is equal to 0, it can be shown that the CDF of the GP, the generalized Pareto, reduces to this, right, which is actually a shifted exponential distribution, right? Okay, and this is the PDF. This is the PDF of the GP, right, and which is the derivative of the CDF is given by this, right? Okay, and this is the quantile function of the GP. So we just set this equal to P and solve for XP. Okay, you set this equal to P and solve for XP, and you will get this as the formula for the quantile function for generalized Pareto, right? And this is the return level of GP, which is related to the quantile function. So in this case, return level is the level that's exceeded once in, on average, once in every t years, and is defined by this, where m denotes the average number of extremes per year, right? And this is estimation part of, this is the estimation part of the GP. Here you only have 2 parameters, not 3, sigma and psi. This is the likelihood function. This is the log likelihood function. And these are the 2 partial derivatives set to 0, right? And you can actually work out the 2 partial derivatives to be this and this. And there is a function in R called FPOT, FPOT, that you can solve to obtain the MLEs for sigma and psi. All right. Okay. All right. So that's the definition 2. And the last, I'm sorry, I'm going through this quickly because I hope you watched my videos already online. So I hope you followed the videos without much trouble. Okay, and this is the last video I did as part of week 3 videos. So this talks about definition 3 of extreme values, right? Definition 3. So here you take the extreme values as the first few largest data points. So it's not just the largest, but the first few largest. So in this case, you have the 5 largest data points. All right. All right. So here I have introduced some notation. So Mn1 denotes the largest, Mn2 is the second largest, and MnR is the rth largest. And there's a result due to Weissman, which says that the limiting distribution, the joint limiting distribution of the R largest data points approaches this as n approaches infinity, where gamma I is given by this. An and Bn are the same as in ETT, right? Okay. So that's and it can be shown from star. This is star here, right? It can be shown from star that the joint PDF of the R largest data points is given by this formula here, right? So this is the joint PDF of the R largest data points, right? And then for estimation, suppose you have R largest data points for up to t years. So t could be say 10 or 100 or 1,000. So this is the R largest data points for the first year, second year, up to t, capital T years. Then this is the likelihood function for the 3 parameters, mu, sigma, and psi, right? And then to obtain the MLEs, you write down the log likelihood, right, which is this one, and then you take the partial derivatives with respect to the 3 parameters and set them to 0, right? You get these 3 equations and solve them to obtain the MLEs for mu, sigma, and psi. Okay, so this is, if you've done the if you've done the partial derivatives, this is what you will get. This is the partial derivative with respect to mu, with respect to sigma, and with respect to psi. So you can solve these equations 1, 2, and 3 simultaneously to obtain the MLEs for mu, sigma, and psi. All right, so this is the fourth video on week 3 videos, right? I know I have kind of rushed through this, but I hope you watch my videos. And do you have questions you like to ask about the videos or anything that I talked about today? Hello, guys. Talk to me. Hello. Are you guys okay or not? Hello? Are you with me? Is everything is okay? Something, okay, return level. Yeah, okay, good. The return level, yeah, the return level is something like, is as I said, is something to do with the quantile function. So the, like if you're looking at, definition 1, for example, right? Definition 1 is, just a minute. In definition 1, all right, okay, if you look at this, for example, here, guys, right, for the GEV distribution, the return level is the level that is exceeded once in every capital T years. Because the GEV distribution applies, I mean, it takes up, it takes only one data out of every year, right? If you have capital T years, if you have capital T years, you have only capital T data points. So the probability that the return level will be exceeded on average once in every T years will be 1 over T. You follow what I'm saying, right? Okay, so because I mean, by definition, it's the level that is exceeded once in every capital T years. But for the GEV distribution, there's only one data point in every year. So out of capital T years, there will be capital T data points. So the probability that x is greater than little xt will be 1 over t. And this is the same as this. And this is the same as saying that the quantile function, in other words, the CDF at xt must be 1 minus 1 over t. And solving this equation, you will get this as the formula for the return level for the GEV distribution, right? And for the GP, it is slightly different, because for GP, you have, in GP, you don't just pick the largest, you don't pick just one data for every year, but you pick like a certain number of exceedances every year. So the formula for the return level for GP is slightly different. You should look at it. Okay. All right, guys. Any other question you have, or is my explanation clear to you or not? I mean, my explanation about well, on average means that it just on average it's just a statistical term. That's what I mean. It's like, I mean, people like to use the word on average all the time. Like, for example, it, like there is a snowfall on average once in every 2 months, right? I mean, so on average it's just a statistical term, right? I mean, it doesn't mean a lot. I mean, it's just a practical term. You don't need to take that as too much, right? So this is the case with the GEV, guys. Now, with the GP, for the GP, the return level is the level that is exceeded on average every capital T years. But because GP is defined differently, because remember in here we are looking, suppose there are little m exceedances every year, right? So over capital T years, there will be little m times T extreme values, right? Okay, so the probability that x is greater than x is greater than little xt will be 1 divided by mt. Okay, all right. I hope you follow what I'm saying here, because the definition of GP, it follows definition 2, right? In definition 2, you don't just pick the only one data, but you pick several extreme values in every year. Now, so if m denotes the extreme values that you're picking every year, over capital T years, you will pick up m times T extreme values, right? All right, so the return level for GP must satisfy this equation, right? And this is different from this one. Yeah, here this is equal to 1 over T because you only have one data point every year, right? One extreme value. But here you have there are m extreme values every year, right? So it will be 1 divided by m times T. All right, guys. Any other question, guys? I hope you follow this, but if I did not make it clear, then I will. I mean, I'm prepared to give you more more explanation. So if you still if it's still not clear, please let me know. Hello, guys. Hello, are you still confused or not? Are you okay now, guys? All right. All right, guys. So I will talk to you guys on Thursday. Is it? Remember, on Thursday we have the tutorial sheet. So please try to go through as many of the problems you have, as many of the questions you can before the class on Thursday, 2 o'clock. Okay. All right, guys. So and if you have any other question, just feel free to email me 24/7 or Zoom me or Skype me or call me. All right. All right. Okay. I'm sorry. Once again, I'm sorry for the delay that was caused to you today. I'll try to fix it before next time. Bye, guys. Have a good night.